Okay, just a technical issue. Now, okay, so now the main point is to prove this result. Okay, once we prove this inequality, once we prove the relation between this system and this system here, what Lagarias and Krasikov did, so let me put that in the comment. So then Krasikov and Lagarias then solve I9 for a certain particular lambda, and deduce from there that pi star of x was greater or equal than some constant delta prime x to 0.84, and that's the best current bound. Okay, because well, the system here is already very large, because the number of variables here is basically 3 to the k minus 1 plus 3 to the k minus 2, which grows exponentially, and the number of equations is I think well, of the order of 3 to the k as well. So we have a bunch of equations and a bunch of variables, so this becomes very, very hard to solve even for a small case. So there's no hope of solving this for very large k to get to something like 0.99. If you think about getting something like this, then probably k has to be with something with something with 3 digits. So yeah, so maybe so definitely you can improve, but it requires a lot of computation power, I would say. And the conjecture is the following. So the conjecture is the following, which is the following. So let lambda be, so let's say lambda k, be the largest for which Lk of lambda can be solved. So the largest lambda for which this system can be solved, then lambda k converges to 2 as k converges to infinity. So that would imply, so this implies that for every epsilon positive, there is some delta epsilon positive with pi star of x being greater or equal than this delta epsilon x to 1 minus epsilon for every x greater or equal than 1. Okay? Which means, this means that I can put an exponent as close to 1 as I like by solving these systems. And the conjecture seems to be true because of the numerical experiments they do, and they explain that in the paper if you want to read. So it seems that you can get as close to 1, and if you want to actually get to 1, then you need another set of information. Probably you need to know exactly what's the structure of the solutions as k gets larger, so you can somehow take the limit in this procedure. Okay. So what we're going to prove basically is that in this class is that this system implies an inequality like this. Okay, and to prove such a thing, what we would do is to create a systematic way of iterating these inequalities here and these inequalities there. And that systematic way will involve certain trees. So for each m, we will associate a certain tree, and this tree will deal with this part here, which will deal with taking these minima and the possible ways these inequalities can be applied. And once you get a handle of these trees, once you understand what's going on, then it will be very simple to derive this bound. But you have the difficult part is to understand how to create these trees that will help you to iterate these inequalities. Okay, but before we do that, and I have to explain what the linear program is. So let me explain just very roughly what's a linear program, what it means to be feasible, and these kind of things. Okay. So let me erase what? Let me erase just the top part here. Let me keep this bottom part for a moment. So we have a longer way to go, so let me explain this quickly. So what is a linear program? Well, a linear program is something very simple. Usually it can be written like this. You have to minimize a certain functional. Let's say your functional is C1 x1. This is not good. We change tens. Go back to blue. Plus C2 x2 plus dot 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 plus Cn xn. So I want to minimize this function, and my variables are the x's, and the C1s and C2 are given constants. Under the restriction that, I have this variable x, which is a vector, would be a row vector. Under the restriction that x dot the certain matrix A is greater or equal than 0, where A here is the real n by m matrix. Okay, so that's the problem. Okay, you want to minimize the functional, it's just the dot product against the C vector, under the restriction that whenever you evaluate the product with this matrix, you get something positive. And this thing here, this positive here, means coordinate wise. Each coordinate of this vector, which will be a vector with m coordinates, m entries, each entry is greater or equal than 0. That's what this greater equal than 0 means. So that's a linear program. Usually, if you look on Wikipedia or so, you see another condition. You see some things like, well, x is actually greater or equal than some vector b, or you see additionally to these other conditions, or x is less or equal than some other vector p. But these inequalities can be added to the matrix A, and you can put just in a simple matrix A. So this is the most simple form of the problem. Okay, so that's what's a linear program. There are a bunch of softwares that can solve this. So Mathematica has one, MathLab has one. So every basic piece of software that you can do mathematics with has already a function that can solve that kind of problems, and you can search more about these kind of problems. They apply in several areas of mathematics, engineering, physics, and so on. Okay. So what's the feasibility linear problem? Well, feasibility LP is basically just asking the simple question is find non-zero x such that x dot a is greater or equal than 0. I mean, that here is the question. But what I want to say is that this problem is just equal to the other one. Because, and that's actually what Lagarias and Krasikov, they write. They actually write, they don't write this, they write a different system, which is what we usually do when we just have a feasibility problem, is that you transform into a standard linear problem. You just introduce a new variable, let's say introduce a new variable. So how you go from this to this, you just introduce a new variable, let's say xn plus 1, okay? And what you do is you minimize just xn plus 1, this new variable, under the assumption that the original vector x dot the matrix is greater or equal than 0, and each coordinate of the original vector xn is less or equal than xn plus 1. Okay, so that's what you do. Just introduce a new variable, and you minimize this new variable under the assumption that the original vector dot a is greater or equal than 0, and all the other original variables are less or equal than the new one. So basically what you're trying to do here is you're trying to find a solution of this, and at the same time minimizing the L infinity norm of the vector. Okay, so from this mapping you can see that these both problems are equivalent. Software-wise, maybe it's better to write it. There are softwares that can deal with this and softwares that can deal with that. Maybe in some softwares it's better to write this, if you have a condition like this explicitly. We do have it like this in our system we want to deal with. So software-wise, maybe it's better to write these things explicitly, because the softwares can usually have different routines to deal with these things. Sometimes it matters, sometimes it doesn't matter. So you have to work case by case. But in our point of view, which is just abstract, they are the same thing. Okay, so now you know what's a linear program. Okay, and there are ways of solving this. You can solve by the simplex method, or you can solve by interior point method, or you can solve by solving the dual. There are a bunch of ways of doing this, and you can do your own research. Okay. So to illustrate how we can prove theorem 18, what I will do, since the subject is a bit technical, what I will do is that I will simultaneously work with the case k equals 2 to see what the concepts we need to generalize to all the case from the case k equals 2. So from the case k equals 2, we would see some pattern, and then we'll see how easily you can generalize to all k's and how this is going to work. Okay, so what I will do now is I will raise the whole board and start with the ideas to so basically the idea is how to iterate this system and the original system for the functions like kn. Please let me erase everything. Okay, so it's getting a bit cold in my office. put this. Okay. So let me maybe write in a corner the system I2. So let me maybe write in this corner here the system with k equals 2, which is the following: phi 2 2 of y greater or equal than phi 2 8 of y minus 2 plus phi 1 2 of y plus alpha minus 2. That is if m is congruent to m congruent to 2 mod 9. So this will always be mod 9, okay? So I will just write it like this: congruent to 2. Oh, sorry, there is no congruence here because I'm just writing the system. This is 2 5 is greater or equal than 2 2 y minus 2 plus y plus nothing. And then we have phi 2 8 is greater or equal than phi 2 5 y minus 2 plus a 1 2 y plus alpha minus 1. And if you realize this is the delicate one, you can already see that because I'm subtracting stuff here. And this, I'm always subtracting something positive because this guy here is negative. But in here, I'm adding something positive because recall that alpha, let me always write, alpha is something like 1.58. Okay, so let me maybe write it like this. Okay, so this is the delicate part. And we have another one, which is this guy, phi 1 2 is just the minimum between phi 2 8, phi 2 2, phi 2 5, and phi 2 8. We know by the previous calculations we did in the previous lecture that we can actually eliminate this phi 2 8 from here, simply because phi 2 8 is greater than this, which is greater than phi 2 1 of y. But we keep just by educational thing. We want to, from this system, derive a way of thinking about how can we generalize the calculations we will do for this system to all the other systems for all the case. Okay. So we split all the things we're doing here in a set of ideas. I think we have 4 ideas. So the first idea, and really, again, I will reiterate that what we're trying to do is finding a systematic way of iterating these inequalities in a certain way that, as we did it for the case k equals 2, that once you iterate in a particular fashion, you get inequalities where all the y's in the right hand side are always, it will be something always like greater or equal than some summation of phi's with y minus something. And so in a way we want to eliminate this alpha plus 1 here because this term is positive. We want always to put y minus something positive. So always keep that in mind. We want to iterate this in a systematic way to reach a point where all the inequalities and all the summations on the right hand side of the inequalities we derive is always something like y minus something, which is not happening here. Okay. So the first idea is to, again, as I said, to use the system to iterate. And the first idea is this: for each m in 3k, I want to associate a tree, which I usually call T, M, but I will just call it T when I fix M, okay? But it would depend on M. Okay, so it's a kind of a possible evaluation tree. And the idea is really simple because, so suppose we start with this guy, then I have this sum and this sum. But this guy here is a minimum of 3 quantities. So it could either be the case that this guy equals this first function here, 2, 2, or 2, 5, or 2, 8. So it branches into 3 possibilities, the second term. And then for each of these 3 possibilities, I have other inequalities to apply. So apply these inequalities to these guys, but again I will get another minimum, which will branch out to another 3 possibilities and so on. So you can already visualize how the tree is going to look like. So for instance, let's see the tree. I will just write what is the tree and you will see what I mean. So let's see the tree for phi 2, 2. Okay, so it's going to, and you also can realize what the notation is. So I have 2, 0. So this guy would correspond to phi 2, 2, y. And then apply the inequality, which I have this, or end up with this guy with a min. Okay? And this min could be 3 things, 1, 2, and 3. It could either be 2 alpha minus 2, 5 alpha minus 2, or 8 alpha minus 2. Yes. So let me write in red. So this term corresponds to that. So this guy corresponds to this, phi 2, 2, y. This guy corresponds to phi 2, 8 of y minus 2. That's why the minus 2 here. And these guys correspond to phi 2, 2 of y plus alpha minus 2. So why this? Because this term here had a y plus alpha minus 2, but this itself was a min. So there's a min node here, and there are 3 possibilities. So this guy is a phi 2, 5, y plus alpha minus 2, and this guy is a phi 2, 8, y plus alpha minus 2. Okay? So that's the tree. So now you know what I mean. The nodes will be either 2 things. It will be something like an m and a beta. So let's say an m prime and a beta prime, where m prime belongs to 3 to the k, and beta prime is something like is some positive integer times alpha minus some other positive integer. These will be the nodes, or a mean node. The mean node I don't define as a proper node, so whenever I say node, I mean this guy, and when I want to say that is a mean node, I will say mean node, which means that this node here. Okay, so this is the tree of decision for these guys, and the idea is to always stop the tree if all the leaves of the tree have a beta which is negative. So if the beta is negative, it means that I arrive to a tree where arrive to a certain inequality where all the y's on the right hand side have y minus something. So what this tree is doing, so maybe I should write it like this. So this tree is implying something. So if I look to all the leaves in this tree, what I realize is that I have something like this. 1y is greater or equal to the min of all the terms that appears in the list. So what is saying that is supposed to be here phi 2 8 y minus 2 plus phi 2 2 y plus alpha minus 2 plus, and then the same thing for 2 5 phi 2 8 y minus 2 plus phi 2 5 y plus alpha minus 2, and then the same phi 2 8 y minus 2 plus phi 2 8 y plus alpha minus 2. So that's what the tree is saying. Okay, and how we decide which terms we put here. So again, this is just me using this inequality here, applying this mean, and for each one of these guys, just replacing each one of these guys in the possible evaluations of this function. Okay, so you get this. Okay, and that's what this tree is informing me. So how can you decide these guys here? How to decide what sums we have to put in the mean? And basically, you just follow the tree. You take all the leaves in the tree. You take. So we will define that later. Let me draw so define that later. How to define what in general. How to define which sums you have to put here. Okay, but you can already guess more or less how you're going to do that in general. The tree for 2 5 is trivial because, again, my idea is to stop whenever I have all the betas. So this is negative, this is negative, this is negative, this is negative. So stop. I don't do anything. I don't apply another one of these inequalities. For 2 5, it stops already because it's just that. So for the tree for phi 2 5 of y is trivial. It's just phi is dot, and then in here is just 2 minus 2. That's it. It's a trivial tree. So again, as I said, the problematic part is this, and the tree of this thing here will be a bit large. So if you imagine in general, there will be a procedure to construct the tree associated within phi km. There will be a procedure, and that procedure will build the tree, and there will be some updating and deletion steps that I will define now. So how can we define the tree for phi 2 8? So in a way, the only thing we can do is just iterate, apply the first inequality. It's just apply the first inequality. So what is the first inequality? Okay, so first you have the 8 here. So you have 8, 0. Okay, and then you either have 5 minus 2, or this term, which is a mean, and that mean is evaluated with alpha plus 1. So you either have 2 alpha minus 1, either have 5 alpha minus 1, or either have 8 alpha minus 1. Okay. So that is what I would say step 1 in the construction, or step 1 in the construction of the tree. I will define these steps later on for all in generality for phi km, but this will be step 1. Okay. And then we realize something, that this generates an inequality just like this, just by the same reason. But the final inequality, which would be something similar to that, is impossible to hold. I mean, this guy will be a minimum of a certain terms, but the last term, which will correspond to taking this guy and this guy here, so the last term will be something like phi 2/8 of y is greater or equal than some min, which the last term will be phi 2/5 of y minus 2 plus this, which is phi 2/8 of y plus alpha minus 1. But if y is greater or equal than 2, and that's, I'm always imagining that y is greater or equal than 2. If y is greater or equal than 2, we prove that this guy is greater or equal than 1. So this term here is strictly larger than phi 2/8 of y plus alpha minus 1. But alpha minus 1 is positive, so this is greater or equal than phi 2/8 of y. Okay, so this term can never be selected, because if it was selected for some y, you would prove that phi 2/8 of y is strictly larger than phi 2/8 of y, which is impossible. Okay, so this term will never be selected, so we can erase it. So this is the deletion process. If I find something here, so I find an 8, and I go in the path up to the roots node, and I find another 8, but with a beta that is smaller, than this guy, I have to delete it, because otherwise I would write an inequality. It wouldn't make sense, because that term in inequality would never be chosen in the calculation of the minimum. So I can then delete this guy. So this is the deletion process that we'll define later. So in a way, this tree here will give you just two inequalities. Either you get this term plus this, or the minimum of this term plus this. Okay, so I already started a convention now. Let me erase this thing. The convention here, is that to simplify notation, I will write just m beta to mean simultaneously the node of a tree or the function phi k m y plus beta. Or, so I will mean this function or a node. They will mean the same thing. So I could say things like that this tree derives inequality like 8, 0 is greater or equal to the mean of 5 minus 2 plus 2 alpha minus 1 and 5 minus 2 plus 5 alpha minus 1. Okay, so I could say something like this. So this was step 1. Let me write here. Step 1 in the creation of the tree associated with 8. Why we don't stop? Because, this leaf has a beta, which is the second guy negative, but this don't, because alpha is greater than 1. So I need to iterate these two terms one more time. Okay, so let me erase this part here. Again, what we're doing here is just creating a set of patterns, a set of procedures that can be generalized to every k. And we're just creating a systematic way of applying this inequalities. Okay. And then later on, we will deal with the linear program in a way. Okay. So step 2 of the construction of the tree associated with 8, 0 would be to iterate these two guys. Okay, so let me write here. And then I have a mean node. And if you are reading the papers that I'm presenting, you will see that I'm using a different notation for the things, and also trying to simplify a bit of the proof they give. So there will be a lot of discrepancies between my notation and the notation of Krasikov and Lagarias. And this is 8 alpha minus 1, which was deleted. Okay, now I have to iterate this guy. So this guy gives two inequalities. We have 8 alpha minus 3. Why? Because we have an alpha minus 1 here, and here we have a minus 2, alpha minus 3, which is good because this guy is negative. Or a mean term, and that mean term will be, the mean term appears with an alpha minus 2 on top of this, which will be 2 alpha minus 3. And then we have here 5, 2 alpha minus 3. And then we have here an 8, 2 alpha minus 3. And this guy just have a one guy, which is a 2 and an alpha minus 3. Okay, so that's step 2. So we apply the inequalities. So that will be the updating process. I'm updating the previous 3, and I have to delete. So there is a deletion process. And what's the deletion process is that, well, and again as before, I eliminated this because in the minimum, the term that this contributes to the minimum will never be chosen. So I could eliminate that. In the same way here. So how can I decide if a term will never be chosen? For instance, the rule here is you take n leaf and you go up in the path to the root. If you find, so this leaf here, for instance, if I find another 5 in the path to the root with a beta that is smaller or equal than this, then I have to eliminate this. Okay, exactly as before. I found this is alpha minus 1, and I found the guy which is smaller than alpha minus 1, so I eliminate this guy. Okay, so what's the other one that I have to eliminate? Well, I guess it's just this guy because in my path to the root I found 0, and 0 is smaller than this because alpha is greater than 1.5. This is bigger than 0, and that's why this 8 here is important. So this guy is bigger than 0, so we eliminate. This other guy was eliminated. Okay. And, okay, so I end up with the elimination process. Is there a step 3? Well, let's see. Is all the leaves with negative betas? Well, here it is, but not here. These two are still positive. I have to iterate one more time. So let me do step 3. Let me do step 3 in the same tree. So I don't need to copy the tree again. So step 3 will be iterating this. So here I would have something like 8 and a 2 alpha minus 5 and the mean node. And the mean node would have a 2, I have a 2 alpha minus 3, but in there is an alpha minus 2, so I have a 3 alpha minus 5. Let me see if this is right. Yes, and all we have 3 alpha minus 5. And this is an 8, 3 alpha minus 5. And in here we just have 1, which is 2, and a 2 alpha minus 5. So this is negative, great. Are these negative? Well, 5 over 3 is something like 1.6, which is greater than this. So it's greater than alpha. So these guys are negative, okay, which is great. Do we have to eliminate these 2 here? Well, this guy is less than this because we did it before. because alpha is less than 2. Is this guy's less than this? Yes, because again alpha is less than 2. So when eliminating stuff, we just need to test the new leaves from the previous leaves. Okay, so that's the final tree. So that finishes step 3. Maybe I should write. So this is so this part here was step 3. And that's the tree associated with 8. This tree here. Okay, we just needed to eliminate 2 things. So again, what is this tree telling us? This tree is telling us a certain inequality that in the same way this tree is telling us that, for instance, 8, 0 is greater or equal than a mean of, for instance, this guy plus this plus this plus this. So this will be one of the instances. 5 minus 2 plus 8 alpha minus 3 plus 8 2 alpha minus 5 plus 2 3 alpha minus 5 ... This will be the first term in inequality, and you have for other terms the same similar inequalities. So okay, so now we know more or less what we need to do to create these trees. Okay, so this was first idea, how to do this for the original K. So let's go for the second idea. The second idea is generalization. How can we generalize this thing? So idea 2. How can we generalize this idea? And the idea is very simple. We just have to create a way to first, for every m, create an associated 3. Second, so that will involve updating procedures. These 3 will be created in a sequence of steps, which in each step will be an updating and then a deletion. And once we have created a tree, we have to understand how can we derive this inequality here from the tree itself. So how can we assign an inequality of this type for the root of the tree? Okay? And you can more or less already guess from the example we did here. So, okay, so first, so how to build the tree for m naught. So suppose now that k is not 2, and you start with a node which is m0, how I create the tree associated with m0. Okay, so I will write an algorithm to create the tree here, based on the system, the general system of inequalities we had. So let me remember what the system of inequalities is in a moment, and let me use the convention already. So that would be m0 is greater or equal than 4m minus 2 plus 4m minus 2 over 3 alpha minus 2, and then we have m0 greater or equal than 4m minus 2, and then we have m0 greater or equal than 4m minus 2 plus 2m minus 1 over 3 alpha minus 1. That's the critical one. And we also have that m0 is the mean between m0, 4m, oh sorry, not 4m, m plus 3 to the k minus 1, 0, and m plus 2i, 3 to the k minus 1, 0. Okay, and this guy is m congruent to 2 mod 9, this is m congruent to 5, and this is m congruent to 8 mod 9. So already like simplifying and shortening the notation here. So that's the system we had in general. So how can we build the tree? So step 0, you start with the tree just as this node, m0. That's step 0. Step 1 is the following. For all leaves, let's say m prime, beta prime, replace it by the following structure. So this is an updating rule. Let me call it this. This is the update rule. Kind of like a cellular automata kind of thing. You have an updating rule for these things. So you replace this node by this tree. So this will be 4m prime, beta prime minus 2, and this will be a mean node. And then we have 3 options, which is 4m prime minus 2 over 3, and then it's beta prime plus alpha minus 2, or either 4m prime minus 2 over 3 plus 3k minus 1, and this is beta prime plus alpha minus 2, and the third one will be 4m prime minus 2 over 3 plus 2i's 3k minus 1, and then it's beta prime plus alpha minus 2. So replace it by this structure if m prime is congruent to 2 mod 9. Okay, again, I'm abbreviating, I'm not writing mod 9 every time. So this comes exactly from this inequality. Okay, if it was m beta here, then it's just minus 2 and then alpha minus 2. So this alpha minus 2 is showing up here. And we also have this 4m minus 2 over 3, which is written here. And you have these additions, 3k minus 1 and twice 3k minus 1. Okay, so just replace that leaf node by this tree if it's congruent to minus 2. And similarly for the other ones. For this guy, you're just going to replace m5 just by a single, and then replace this by a single thing. So similarly, for m congruent to 5 or 8. So if it's going to be 5, it's going to be just a tiny thing like this. And if it's going to be 8, it's going to be something very similar here, but instead here will be 2m prime minus 1 over 2, and this alpha minus 2 will be alpha minus 1 instead. So it will be a similar structure. So that's the updating rule. For each leaf you had before, you just update that thing, you replace by this structure. Okay, so that's the updating rule. Let me write the deletion rule. So let me write this thing here. So step 3 in the construction is is the following: for all leaves is that how we write leaves? Yeah, maybe it isn't. So for any leaf, let me write with this as well. For any leaf, n prime beta prime, if in the past history, and what I mean by past history, I mean that you have a leaf here in a tree and you go up. There is a unique path that makes you to go up to the root node. In the past history, so instead of writing like this, like if in the path up to the root node, let's say m0, we find another m2 primes beta 2 primes with the same m, so m prime prime equals m prime, or better to say congruent to m prime 19 mod 3k. Okay, but I'm always using arithmetic mod 3k here for this ends. So if I find m prime prime equals to m prime and with a beta prime prime which is less or equal than beta prime. So I went up, I go up, and I find the same number m prime at a certain point. So the drawing will be something like this. So I have m0, and then you have m prime beta prime, and some other things here. And then you have here m2 primes beta 2 primes, and the tree can go on. So you are here, and then you go up and you find another guy which is the same m, but you have a beta which is greater or equal, and you have a beta the drawing is in the opposite direction. So this is the leaf, this is the leaf, and this is the 2 primes. So this is the leaf. I go up and I find another guy, and this other guy has the same number m, but the beta is so 2 was right. This beta 2 prime is less or equal than this. That means that when you went from this to this part here, you found the same m, but with the larger beta prime. Larger. So if you find this, then you delete. Then delete. Okay, so this is the deletion rule. This is the deletion. Which was exactly what we did. Here we found an alpha minus 1 in this example, and this alpha minus 1 is greater than 0, so that we remove. We found the 2 alpha minus 3, and the other one in the path was a 0, and 2 alpha minus 3 is greater than 0, so remove. So what I'm doing here is I'm forcing that when I go down in some path, if I find in this path 2 numbers which are the same, then the betas decrease. Okay, so this is I'm forcing the tree to have this property. Okay, and the final step, which is step 4 in the build-up, is that either all leaves, all leaves, I think it's leaves how you say, but anyway. Let's say either any leaf has a beta which is less than 0, which means you stop, then you stop, then you finish with the process of creating a tree, or go back to step 1. So introducing a loop in the algorithm. Either you stop or then, so this is a test, if I have to stop the loop or not. If all the leaves have negative beta, then stop the loop. If not, I go back to step 1 and reinitiate the process. Okay. So now we know a way of creating the tree. Okay. My claim is that the tree you're going to create is going to be finite. At some point, all the leaves will have negative beta. So this process will not go forever. That's my claim. So let me write that as a lemma. I will not prove this lemma now. I'll prove in the end. After I prove the main theorem, I will prove this lemma. You can already guess more or less why this is true. But let me state this lemma.